Today we'll talk about drones, and we'll basically do the whole work that we did in the past half of the semester, or more than half the semester, the past 10 weeks, I think. We're gonna do it condensed for the drones in 2 hours. So we're gonna talk about kinematics, about dynamics and control, and in between, in order to understand a little bit of the dynamics and how these things fly, we'll talk a little bit about aerodynamics and propellers and whatnot. Right, so the structure for today is basically this. Start with kinematics, talk a little bit about aerodynamics and propellers, and then how these applied in the drone design and the work principle, flight principles, and how do we use this to model the drone and eventually control it. So this is what we have seen so far. Now we talk about different types of robots. It's grayed out because we talked about manipulators, and we will talk about drones, we'll talk about mobile robots, maybe about underwater. We'll see. If the last lecture will do a summary or will do underwater. Probably I'll send you a poll to choose. All right. So what are we talking about? We're talking, when we say drones, it's a rather big category of flying robots. Okay. And today we'll talk about the subset of those. So we'll talk about specific quadrotor drones. So it's drones with 4 motors, basically 4 rotors, right? So it's something that looks like that or like this. I brought a physical thing because it will help with the rotations. This is like one of the most typical designs for drones. You for sure have seen one of those in real life. Maybe you even own a couple of them. But why is it so popular? Why 4 motors? Why 4 rotors? What? It's stable. Okay. It is. Yes.
It's easier to maneuver.
Easier to maneuver than
3 motors, for example.
Okay, but harder than with 5, I guess. No? Or with 6?
What?
Or with 6?
I don't understand.
Or with 6? You say it's easier than with 3 motors. Why?
Because you can just steer, driving the motors higher or lower on each side. So you can just bend just by hitting the motors.
All right, so then why 6 motors is not giving you even more easiness in maneuvering? Because if 3 is here, let's say in the easiness, 4 is here, then 6 is probably there, not...
It's easier to calculate what each motor plays for the connected.
Easier than what, again?
Easier than less than 4 or more than 4.
So 4 is the sweet spot of, I don't know, everything.
It's like in robot arms, like adding more motors, usually more degrees of freedom usually means easier maneuvering. But
All right.
depends on where you add them.
So if we have 4 motors, then we have how many degrees of freedom?
6.
That does violate what we talked in robot arms, like, okay, 1 actuator. All right, we'll see. We'll come back to this question. Since it's not clear and you're not convinced, we'll come back. But it's a nice number, 4. Right. Let's see what possibilities we have these robots and how many degrees of freedom we actually have. And in order to discuss kinematics, we need some frames. So again, we'll use the knowledge we have from the transformation matrices in the first lecture. And we will describe kinematics of the drone, of the robot, as the transformation between a fixed frame, a reference frame, in this case we'll call it the earth frame, E, and a frame attached to the end effector of the robot, which, for the drone, it's basically attached somewhere at the body of the robot, in a convenient location, typically at the center of mass of the drone. And that we call it B, the body. This is just a naming convention, right? And we have some axes, All right, so for the Earth frame we have X, Y, Z as typically, and then we have the three rotations, phi, theta, and psi. It's the Euler rotations that we learned also for robots. And then on the drone, on the robot, we have again another frame attached here. Here we use different names for the axis so that we don't confuse them with these ones, and also we'll see that they represent something slightly different. So we have U, V, and W, and the three rotations is P, the rotation around the U axis, Q, the rotation around V axis, and R, the rotation around W. Okay, so U, V, W, P, Q, R. All right. So basically, X, Y, Z represent translation along the principal axis on the Earth frame, right? And we have the phi, theta, psi, which is the rotation around the axis of the Earth frame. Now, U, V, and W, they represent velocity on the axis of the drone frame, of the body frame. Okay, it's not positions. Right, and PQR are angular velocities around that frame. So why do we talk about velocities in the body frame and not positions? Any feeling?
I mean, the drone itself cannot translate on the only up or down.
It cannot translate like this?
It can.
But if it was just like this, it would be a rocket,
I mean, to do
a spaceship.
that, it has to have a tilt.
Okay, that's another thing, but yes, it can translate like this, but it does not translate relative to its own frame. So then, yeah, I mean, if we talk about translations in its own frame, it's kind of meaningless, right? So then we talk about the velocities on that frame, and it's also what we will see later on, it's what we actually control. It's what we call, the drone is basically a non-holonomic system, right? So we don't affect its position, but we affect the velocity, and by the integration of velocity, we change the position, whatever. Right, we group these coordinates, because we're going to use them a lot. We group them in some weird letters here. So we'll do a little bit of Greek today as well. So the three translations in the Earth frame, we call them xi. You should know this xi from Jacobian. It's xi, not theta. And phi, theta, and psi, the three angles in the Earth frame are called eta or eta. I don't know how you call this in English, right? And yeah, these two together are p. And then we have small p, or Greek pi, basically. It's the three velocities in the drone frame, v, u, v, and p. Sorry, here I have it should be w. My bad. And rho is p, q, and r, the three rotations. And then we group these together into a capital V. Right. So when talking about kinematics, what we care in the end is the description of these two frames, right? As we saw with the manipulators, we had the transformation from the base frame to the end frame and the vector frame, and we would calculate by the subsequent transformations between subsequent joints. Now we only have two frames basically, right? So it's a bit easier in that respect. And if we talk only about the orientation, because for the modeling aspect, this is the only thing that will affect our model. Basically, the dynamic model of this drone is invariant of where it is in space, so the x, y, z coordinates, right? It's the same model, behaves the same way. But, you know, the way it's oriented will affect some things as we see. So if we talk about the transformation, just the orientation part from the Earth to the base frame, it's basically the Euler transformation matrix that we've seen also for manipulators in the inverse kinematics lecture, where we have basically these cosinus sinuses of phi, theta, and psi. So here, this notation, I remind you, cosinus of theta is c of theta, just to keep things fitting in a slide. So if I know these angles, phi theta times c, I can calculate basically what's the orientation of the two frames, Earth and robot. All right? And this is useful because it basically can convert the velocities from the robot frame, which if you remember we symbolize with pi, the linear velocities, okay, u, v, and w. We multiply with this transformation to get the velocities in the Earth frame. This is pi, it's already velocities, xi is with a dot because xi was position, so it's xi dot is velocities, right? Good. All right. For the angular velocities, we have a slightly different matrix that we need to multiply with. So this gives us the transformation between the angular velocities in the robot frame and in the Earth frame. And we can use this multiplication to transform from rho, which was the angular velocity in the robot frame, to eta dot, which was eta was the angles in the Earth frame. So eta dot is the velocities in the Earth frame. So in the end, we have the forward kinematics described with these two parts, with these two equations, like this. So I have xi and eta, which was p dot, equal this matrix here with these two submatrices, p and rho. This is basically like the Jacobian for the robot, right? Why Jacobian? Because it transforms velocities from one frame to another. So in a way, it's a Jacobian. Okay, so we have velocities in the robot frame and we calculate them in the Earth frame. All right. So this is what the forward kinematics, or the analogy of the forward kinematics, what we saw for the robot arm, but applied in a robot, in a flying robot, right? It's simpler because we only have two frames involved, and it's very abstract in the sense that now this phi theta times c can have any value, while before we had the joint coordinates getting involved and so on, but it's the same thing. If I know these joint coordinates, you can think of the three angles as the joint coordinates, I can calculate the orientation of the drone. The position, again, is not important in this modeling because it doesn't affect at all the dynamics, basically, of whether the robot is here or here or here. It's the same dynamics. So we don't describe it. Right. What about the inverse kinematics? So if this is the forward kinematics, what is the analogous of inverse kinematics? How do I calculate inverse kinematics?
We multiply by the inverse of the Jacobian to
Wait, the angles of the Jacobian, what? Once again?
Multiply with the inverse of the Jacobian to the left.
With the Jacobian being this matrix, right? So yeah, this is basically my whole Jacobian. You can think of it as the linear and the angular Jacobian here, right? So yeah, this is the whole Jacobian that gives me velocities, linear and angular velocities. So it's as simple as that. Basically, if I want to calculate the inverse kinematics, I do inverse of the Jacobian, because this is a linear relationship. I mean, for specific values. Right? This is a system of linear equations. These elements here are not linear because we have sinus, cosinus, and so on. All right, but the unknowns of the system, they're just multiplied with them. We don't have powers. We don't have anything. So it's actually a linear system of equations at a given configuration. So we can just invert it by inverting the matrix. As long as this matrix is invertible, then we can calculate the inverse, right? So yeah, here if you notice the indices are swapped. So here I have the rotation from body to Earth and the Jacobian from body to Earth. So this is the inverse of what we had before. But the first part is very easy to calculate. It's basically the transpose. It's something we mentioned briefly when we're talking about transformations, that the inverse of the orientation part is equal to the transpose. Whatever, I remind you here. So in order to calculate the inverse of this, I just transpose it and it's there. But Jacobian, for the angular part, then we have to really calculate the inverse. All right? So we covered forward inverse kinematics like in 3 slides, easier. Some stuff are easier, some stuff will be a little bit more complicated. Right. Now, in order to move on to the next part, which is the modeling, the dynamic modeling, we need to understand a little bit how these things fly. Right? And in order to understand how they fly, we need to talk a little bit about aerodynamics and more specifically about airfoils. Airfoils is basically a section of a wing, like the airplanes have, right? Or in the end, it's anything that goes through fluid, and more specifically through air, if it's an airfoil, right? So anything can be an airfoil. And basically, what makes airplanes fly and what makes them fly is the development of some forces on the surface on these airfoils, which they're part of a wing. And let's see what forces do we have. First of all, we need something to make that airfoil move through air, through the medium, right? In the case of an airplane, it's the engine pushing the gas behind and pushing the airplane in front, right? So we need basically a thing that we call thrust. So this is a force that moves this airfoil in front relative to the medium, right? Then we have the weight. That physical object has some weight, right? And due to the angle of this airfoil relative to the movement direction, okay, which is something we call the angle of attack. So basically how, let's say if the air is flowing in this direction constantly, what is the angle that the airfoil will attack the air, right? We have 2 more forces developing, the lift and the drag. The lift is a force kind of, no, actually it's not kind of, it is perpendicular to the movement of direction, right? And the drag is in the opposite direction of the movement direction, right? So these 2 are perpendicular and the lift is perpendicular to the movement direction, all right? And based off how we put the angle of attack and the movement direction of the weight, we try to keep the lift kind of opposite from the weight. All right. So if we sum all these forces, we will end up basically with one resulting force. The sum of all the forces will guide, which way the airfoil eventually will move, right? So typically, the drag and the thrust are in kind of opposite directions. So thrust is aiming to cancel the drag, which is basically resistance from the air. You can think of it like this, right? And lift is, as I said, kind of in the opposite direction of the weight. And thrust should have a bigger value than the drag, obviously, otherwise the airplane would go backwards, not forwards, right? And if we want this wing or airfoil to fly, to go up, then the lift has to have a higher value than the weight. So eventually, if these 2 are bigger than these 2, I will have a force developing, I don't know, in this direction, more or less. Let's try to draw it. And maybe even higher. All right, so it will make the airfoil go forward and slightly upwards. All right, clear? So what's important is this lift and the drag. And how can we affect this lift and drag? We have basically 3 things that we can do to affect it. One aspect that we can change to affect the lift and drag relationship to the thrust is basically the design of the airfoil. How does it look like? Is it a sheet of paper? Is it a square? Is it a cylinder? Is it like a wing shaped? Whatever. All these objects will create some lift and drag. in order to have the condition that I said that the lift has to be bigger than the weight and the drag smaller than thrust, we need to have a thing that looks like a wing, basically. Why? That's another story. So that's one thing. The second thing that we can do to affect this lift and drag ratio is the angle of attack. So for the same design of the airfoil, if we change the angle of attack, we get different ratios of lift and drag. Right? For, let's say, a small angle of attack, I will have some lift and drag, so small drag but also small lift. As I keep on increasing the angle of attack, I keep on generating more lift without necessarily creating more drag, until a certain moment when I have like too much of an angle of attack, where I have a thing called flow separation and turbulences developing on the top side of the airfoil, where I start having a lot of drag and not so much lift. Right. So this is, you know, the airplane, whatever, I'm not gonna go there. Right. So the second thing we can affect is the angle of attack. So design angle of attack. And the third thing is the velocity. I don't think I have a slide for that, but basically for the same design and for the same angle of attack, the velocity will affect again how much lift and how much drag I will have. Okay? Again, it's up to a certain point, the more velocity, the more lift and the more drag I have, until at some point, you know, I start again having flow separation and drag becomes too much compared to lift. Whatever. So velocity, design, and angle of attack. Right. Good. Now, in drones, we don't have wings, we have propellers. Right? This is what makes the drone fly. And how do propellers look like? They look something like this. Probably you've seen one from close by. It's basically, it's a blade, but it's twisted, right? So here we have a view of the propeller from the top, let's say in this view, all right? And here we see some cross sections, which shows me this, you know, twisted nature of the blades. Now, why are these twisted and they're not just flat blades? Right. We have an angle of attack everywhere.
The influence of, due to the influence of drag and lift.
Yes.
If it's like straight line, the ratio will be equal, I guess. But
if I have a certain angle of attack here, why can't I have the same angle of attack here as well?
Because that part moves faster than the other.
Right, so we have the higher velocity, right? So in order to have, we try to have basically an equal distribution of the lift along the blade, along this blade, right? But because these outer parts rotate much faster because of the radius, right? If I had the same angle of attack, I said earlier that velocity affects the lift and the drag, I will have a higher lift here than here, right? And this would create basically bending moments, so the blades would deform like this, right? So in order to keep basically as much as possible equal distribution of forces on the blade, since I have higher velocity on the edges, I need to have smaller angle of attack. That's why, as you see here, the angle of attack is smaller, here is bigger. Also, the inner parts of the propeller are thicker because they will have to counteract all the torques that are developed in the end, but that's another story. For these ones, you don't really see it. They're kind of the same. All right. So a propeller is basically many airfoils with different angles of attack just to counter for the different velocities that the propeller will have. Great. Now, what's important to notice here is that each of these little airfoils will generate a lift, and the lift will be basically in this direction, ape. So this is lift. Okay. and here as well. But the lift here points upwards and here downwards, but it's actually all on the same side. So when this one rotates, the lift will always be pointing towards you, both from this side and this side, right? Good. But they also generate a drag, so like this. All right. If I plot the drag in this view, the drag will look like this, basically. For the propeller rotating like this, drag will be pointing downwards. Okay? Can you visualize it? So when this thing rotates like this part is pulling the blade a bit behind when it's rotating due to friction.
So basically that's the effect of drag, no?
Yes, exactly. And on this side it will be the other way. So sorry, here I forgot to put an arrow. So when this rotates like this, I will have drag developing here. All right? Now, what's the combined effect of all these lifts and all these drags? So the lift, if I add all these forces, I integrate basically all these little forces over the whole area, I will have a resulting force pointing towards you or pointing upwards, right? This will be what will eventually make the drone fly. Now, if I take the integral of all the drag forces, so these ones pulling like this and these ones pulling like that, I will basically have a torque around this axis. Because here I will have these forces acting over a distance around this axis, right? So all this, if I add them, I will have basically one bigger force times this distance. I will have a torque, right? And the same thing here. I will have a sum of all these forces over this distance. I will have a torque. And this torque will basically have the opposite direction than the rotation. So if this propeller is rotating like this, generates a lift, then I will have a counter torque around this axis of rotation. It's like the resistance of the air. Okay? Good. That's all we need to know in order to figure out how these things fly and move around. So, this is a schematic, a clear schematic I made here. I have this propeller, it rotates as the blue line, and it generates a torque like the dot red line, right? Torque, I don't remember if we talked about it for manipulators, but basically it's a rotational force, right? A force acting over a distance, and we can calculate it as a vector eventually, which is, the vector is at the axis of rotation, that's the direction, and the length is the magnitude of the torque. Right? It's the same thing as angular velocity, if you remember, or angular acceleration. We have an axis of rotation, and the torque acting around that axis will have the direction of the axis of rotation, and the magnitude will tell me how much is the torque, the magnitude of the torque. And obviously I can have a positive or a negative torque in both directions based on if it's like this or like this. All right, so in this case, if the propeller is rotating like the blue line, I have a torque like the red dotted line, which eventually is represented by a vector like the red vector pointing upwards, following the right hand rule again. So if this thing is rotating like this, the torque is like this and it's pointing towards you, right? And at the same time I have the green arrow, which is the lifting force. That's how we understand these ones. I put it on one motor because soon we'll see it on 4 and it's going to be more things to understand. Now, we said that the lift and drag are proportional, or anyway related to velocity, and in the end we can calculate this force, the lifting force and torque, drag torque for its propeller as b times angular velocity square for the force and d times angular velocity square for the drag. B and D are design parameters that have to do with the shape of the blade and whatnot. We're not going to go there. And this is also a simplified model. Of course, there are more accurate models on how to calculate the lifting force and drag torque of a propeller. But for our modeling, this is more than enough. It's basically proportional to the square of the angular velocity. Right? And what I said earlier, like the faster this thing will move, the more lift and the more drag it will create. Up to a limit, this is correct, but higher velocities things are not that simple. Clear? Are we following? Great. Now, what if we put 4 of these together and we get a quadrotor? What do we have? I have 4 of these motors, and if you pay attention, you will notice that they don't all rotate the same way. Those of you that have played with drones, you have noticed that already, that basically the motors rotate in pairs. So I have 2 motors spinning counterclockwise, and I have 2 motors spinning clockwise, the way you see it from here. All right? That's what you see here with the blue arrows. You see how the motors are rotating, and you see that they are opposite. Obviously, they all generate a lift in the same direction. So they don't just rotate the other way, but also the propellers, if you see them, they are different. They're mirrored. You will see that this is mirror of this one. Right? So this is made so that it generates lift when it's rotating like this, while this one is made to generate lift while it's rotating like this. Right? So then eventually we want all of them to create lift. We don't want them to pull the drone down. Right? So they rotate inverse, but the lifting force is in the same direction, but the drag forces are always opposite from the direction of rotation. So here for this one, for instance, that rotates in this way, the drag is opposite. And here, again, the drag will be opposite. So I will have basically these 2 rotating like this and generating drag like this, and these 2 rotating the other way around and generating drag the other way around. All right? This is essential. We'll see immediately why. We'll talk a little bit, okay, how do the motors have to move so that the drone flies in certain ways? And we'll basically see 2 different configurations that we typically consider, the X and the cross. The only difference is how the frame is oriented relative to the motors. All right, so here you see if I have the drone, basically X and Y will be like this. This is the X configuration, yeah, because it looks like an X. While for the plus configuration, it's basically like this. And so it looks like a plus. Or you can think of it like the axis is moving or the robot is moving, it doesn't matter. All right. So let's start with the X configuration. And we need to figure out how do I have to move the motors, what should be the conditions for the motors, and in the end we're talking about the velocities of the motors. So what should the velocities of the motors be? Why the velocities? Because we saw that affects the forces generated, right? So what should the velocities be so that we do certain motions? So let's say I want to move just up and down. I want to move in the W direction, if you remember, that was W. How should the motors move so that I don't move in any other way and I just move up and down? One by one, go ahead.
The lift coefficient to be high, for example, motor 3 and 1 to be
Motor 3 and 1 should be on, and the others off?
no,
All on? And then, I don't know, they should have the same velocities, different velocities? The same velocities? Any other opinions? You all agree? Right, so that's the truth. The truth is out there. That's correct, right? So in order to move just in the W direction, so up and down, I have to move all the motors with the same velocity. And based on that velocity, it will basically determine whether it will go up, down, how fast it will go up or down, or if it's going to stabilize on. Now, why do we need all the motors to have the same velocity?
Because otherwise we would have tilt that would cause unknotable.
All right. I would have tilt. Why would I have a tilt?
Because the motors would spin unevenly.
All right. So, sorry?
We would have no lift on some.
On some side. Right. So I'll draw the same drone on two sides. So this would be, let's use colors. Right, this would be W and Y, yeah, U, sorry, and V is going in the board, right? And then if I see it, basically seeing the drone like on this side, then here I will have the force from motor 1 and the force from motor 2, 4. And you should imagine this being on the same spot. Maybe I should just do them on the same spot. All right. And here I will have F2 and F3, right? And I will draw the same drone, but now from this side. All right, so now I see W again and V. Sorry, I forgot to write W here. So here I see it like this, here I see it like this. So if this is V, then I have here force 1 and 2. And here I have force 3 and force 4. The lifting force from each one of the motors, correct? And I want this to be equal, right? So it's stable and it doesn't tilt. The sum of these two and the sum of these two have to be equal. So in the end is basically F1 plus F4 equals to F2 and F3. Okay, they can be different between these two, but the sum of them has to be the same, right? And then I have to have F1 plus F2 equals F3 plus F4, right? Now I remind you that Fi was B times omega I squared. So in the end I can write B omega 1 plus B omega 4, la la la, but B will get out of the equations, and in the end I will have omega 1 plus omega 4 equals omega 2 plus omega 3, so the velocities, the squares, okay, omega 1 plus omega 2 square equals omega 3 plus omega 4. All right, so that's the condition in order to not tilt, basically. Does that have a unique solution when omega 1
And also, if two opposing velocities are equal, and the other two are equal to 0. But I think that only works on paper.
So if two opposing velocities are equal,
The other
meaning
two are 0.
F1 and F3,
F1 and F3.
yeah, if F1 is equal to F3 and F2 is equal to 0 and F4 is 0, so if this is 0 and this is 0, then this will be equal to F1, correct? F4 is 0, and this is equal to F3, correct? And then because F2 is 0, this will be equal to F1, and this will be equal to F4. So I can also have two of them off and then the other two rotating, right? And it will still fly up and down, correct?
On paper it works.
On paper it works. Sorry? Theoretically, it should work if we just consider this. However, there is one more thing that we're missing, and it's the torques generated, right? So we don't have just lifting forces generated, we also have torques, right? And what happens in this case? Let's say we have just omega 1 and omega 3 rotating. They both generate torques in the same direction, correct? So then if we do this, then the sum of these two torques will generate a torque, and the drone will also start spinning.
It would still go up.
It will still go up in the perfect scenario that these things are perfectly aligned and all these things. The masses are also, the center of mass is really here and here, which is not the case, whatever. But yeah, so yeah, in paper it would work, in physical it wouldn't work, but even that it would still rotate. So we will not have a pure motion up and down. Because on top of these two, basically, they will generate some torque, it's better seen there, that would make the robot spin, right? So what else do we have here? We have torque. I have basically two more equations here for these two. Torque 1 plus torque, sorry, it's not with a plus, so I have to make sure that the torque cancel out. So I have torque 1 plus torque 2, torque 3, have to be equal to torque 2 plus torque 3, torque 4, sorry. Why these two pairs? Because torque 1 and torque 2, torque 1 and torque 3 are in the same direction, and they have to cancel these torques, right? So I have an extra condition here, which basically these, how do they translate? Again, here I have the torque was d omega square, so I have, let's write it here, torque I d omega I square, so this will get to be omega 1 square plus omega 3 square equals omega 2 square plus omega 4 square. And I think this has a unique solution for when omega 1 equals to omega 2, omega 3, omega 4. Right. So in order for the drone to just fly up and down, I need to have all the motors spinning in the same velocity. And then if they are the same velocity, they will cancel each other out, the torques. All right. And then the magnitude of the velocity will determine what is the total force that will determine if it's going to go up, down, what will be basically the acceleration. All right? Clear? Yes?
Theoretically, in the case, if we have two motors that are off, like we only have two motors working, and they generate the same lift because they have the same velocity square.
Yes.
But they rotate in counter directions, so
Yes.
the torques will be zero.
Yes.
The torques will be
Theoretically. So if we have these two off and these two spinning,
diagonal.
diagonal. But through the design, the diagonal ones, they spin in the same direction. Right? Always. Yes, if the diagonals would spin in the opposite directions, it would work, but it would complicate things, because then if this would spin in opposite directions, these would have to spin in opposite directions too.
But if they're off.
And then you would end up having them like this. These two spinning the same way, and these two spinning the other way. I don't know if it would work. I have to think about it. Maybe. But yeah, now in this case where these two spin the same and these two spin the same, if I would deactivate these two, yeah, this would not generate any drag, but then I would have an imbalance. So it would still not do the thing I wanted. All right. Actually, what you say works. There are some kind of helicopters, the Chinook, if you know them, that they have two propellers like this. You know, helicopters have one propeller like this, one like this, typically. Again, it's for the same reasons, to counteract torques. Right? There are helicopters that have two spinning like this. They're called Chinooks, I think, or at least one type that I know. All right. How, now let's move on because we don't have too much time. What are the conditions so that I have rotation around the x-axis? So I rotate basically like this, around this axis. So in the end, it's basically this rotation. How should the motors rotate so that what are the velocities so that I have this rotation in this figure?
Two motors that are on the same side should have greater velocities than the other.
Yes. So F1 plus F2
Should be greater
bigger than F2 and F3. That's one thing, but also, and that's why actually why we need the opposite direction diagonally, so we can do this kind of motion. F1 and F2 spin in opposite directions, right? Omega 1 and omega 2, they spin opposite directions, right? So these two spin opposite. So they have to have the same velocity so that their torques cancel each other out, okay? So these two have to be bigger than these two, all right? But they have to be equal. These two have to be equal. And these have to be equal. So that the torque from this one cancels the torque from this one. And then I have just the lifting force that is bigger on this side than this side and makes this movement. Okay? So I need to have omega 1 equals to omega 2 and different than omega 3, which is equal to omega 4. Okay? If I had what you described earlier, the two same spinning on this side, I wouldn't be able to do this because they're spinning on the same direction and then they cannot cancel each other's torques. These two have to spin in the opposite direction in order to do this, right? Yeah, I would be able to just move up and down moving these two motors, but I wouldn't be able to tilt in this way. Probably I would be able to do it in another way, yeah. Okay. Just to move on, if I want to move in the other direction, so basically if I want to move in this figure like this, then I need to make sure F1 omega 1 equals to omega 4 and different than omega 2, which is equal to omega 3. Again, these two move opposite, so they have to cancel each other out, the torques. So this is the main thing. I can go up, down, and I can tilt. What about this rotation?
You just have to make the motors spin slower, so the other diagonal motors will spin slower. So
And I don't want to go up and down, right? Okay. So diagonal motors have to spin slower. Why?
yeah, one in order to have a bigger torque on the other two in order to spin.
One of them to spin slower.
No, two of them.
Two of them. The diagonal ones. Right. Correct. So the condition is that omega 1 equals to omega 3. So we have the two opposite ones being equal and different than the other pair also being equal. Why is that? They have to be omega 1 and omega 3 equal and omega 2 and omega 4 equal. So basically these sums are the same. So basically here I have F1 plus F4 have to be equal to F2 plus F3, all right, and F1 plus F2 have to be equal to F3 plus F4, right, so I don't have any imbalance here or here, right, and if omega 1 is equal to omega 3 and omega 2 is equal to omega 4, then this sum will be equal, and the same thing here of F1, F3, F2, F4 is going to be equal, so I don't have any imbalance, but they have to be different so that the torques they generate are different.
And how isn't this also generating movement up and down?
You have to tune basically, right, wait a bit. So you can tune, this sum can be, so these two sums have to be equal to the weight, correct? So that it doesn't move up and down, right? And I can split this force into a smaller F4 and a bigger F1 and a smaller F3. Oh, sorry, F2 and a bigger F3. Right? So I can choose how this I have to split in two. Half of it goes here, half of it goes here. Right? And then I can choose this half how I distribute to the two motors. Of course, there are limits, right? Because I cannot put this to negative, probably. I could, actually, yeah, true. But then I will have an opposite torque as well, which is not bad, it would help. Yeah, so I could even put it theoretically downwards. So yeah, in theory I can do pretty much any combination. But that's how you can keep it stable from flying up and down. It's all about balancing forces. All right? Now we talked about translation and 3 rotations. 1 rotation, 2 and 3. What about the translations? How do I make it go left and right?
You just keep the rotation for a longer period.
So I have to do this basically, right? So a translation on u, or a velocity on u, is basically equal to q dot. I have to have this, right? And a translation on v is coupled to this thing. So how many degrees of freedom do I have? 6. What was degrees of freedom? How many independent movements do I have? How many independent movements do I have here? 4. Because the translation is coupled to the rotation. I cannot translate without rotating. And I cannot rotate without translating. So the moment I rotate, it will translate. Right? So these two pairs, they're coupled. Right? So they're not independent. So I only have 4 degrees of freedom, as many actuators as I have. If I want to have 6 degrees of freedom, I need 6 motors. So why don't we have 6 motor drones? Heavier? Expensive? So this is a compromise. It's a good enough for the use cases that we have, right? There are 6 motor drones for specialized cases, and those basically allow translation without rotation, right? But for the typical use cases of drones, this is typically not a problem, and the trade-off between more expensive, heavier, which results in other problems in drones. Heavier drones means lower running time and whatever. If it crashes, it kills more people, and in some cases that's an advantage, not a disadvantage. Okay. Anyway. But seriously, I mean, this is part of the engineering design of drones, right? So in the end, this seems to be like a good balance between flexibility, maneuverability, and cost, lifetime, and so on. Yes?
But if you have very precise control and a very good model of the drone, I think you can be like almost perfect.
You can cheat nature.
No. But I've seen like those drones from racing competitions.
Yes.
Like very specialized, and they almost have translation. Like
almost. For engineers, it's
yes.
Yeah, it's translation, and that's what we'll do later on after the break. You will see that basically we also say like, okay, we can ignore some parts. Yes, in the end you can do like very small movement. It's not about control, it's about how fast you want the translation, the rotation, and you can you can end up with a higher translation, but you always have a bit of rotation. They're not uncoupled. Because you have 4 motors, you cannot have 6 degrees of freedom with 4 motors. Prove me wrong. Very quickly, I said we have 2 configurations. It's the same story if we have the other configuration. I'll put it here so you see it during the break. It's slightly different conditions because we consider the frame slightly rotated, but it's the same idea. Nothing changes. Any other questions?